Hello friends, I am Rajat Batra and today we are here to study a most important topic named as binary search. आज हम binary search के बारे में बात करेंगे. So before proceeding further, let's see what we are going to study. Firstly, we will understand our question properly, that what binary search want from us. Then we will understand the need that we are doing binary search, we are spending our time learning binary search, then what's the need for that. Next, we will learn about the approach, how to do binary search. Then we will understand it with the help of real life examples, pseudocode and Tryton. Then we will actually code our solution. Then we'll talk about time complexity and subject space complexity. And then we will learn some key point that we need to refer to whenever we are asked about binary search. Means it is a full-on package to binary search. In this video, we will learn everything about binary search that you need to know for your interviews. So now, let's understand our question first. We are given a sorted array of integers having n elements. Means we are given an array having n elements and a key value x. What we need to do is, we need to find this value x in our array and return the index of that. Your task is to search for the given key x in the given array and return the index of the key if it is present in the array, and otherwise return -1, indicating that key value x is not present in the array. So let's understand the question properly with the help of example. Here we are given an array ARR whose elements are 10, 20, 30, 40, 50, 60 and so on. It's a sorted array, so we can apply binary search. And the key is 30. We need to find out the index of this 30 in our array. So our output is 2, 0, 1, 2. So output is 2. In the next case, we have the same array and now we want to find out the key x is equal to 5, which is not present in the array. So we return -1. Similarly, in the next case, we have an array sorted array ARR and we need to find out the key x is equal to 1. Here x is equal to 1 is present at index 0, therefore our output is 0. Now I hope you have understood the question very much. Now let's understand why we need to study binary search. What's the need of studying binary search? If I ask you to search an element in an array, what you will do? You will traverse the array linearly. Suppose you have an array 1, 2, 3, 4, 5. I ask you to search for 5 in this array. What you will do, you will keep a pointer and you will start from here and you will compare it with our 5, with our key which is 5. Is it 5? No. Is it 5? No. Is it 5? No. Is it 5? No. Is it 5? Yes. Then you return I, that is index 4. But how much time do you take to do this? You are traversing the entire array in the worst case. So if we do a linear search, our time complexity will be order of n. So to reduce this time complexity, we use binary search to find an element in a sorted array. We will read this. If we do the linear search and compare each element with the given key x, in the worst case we need to perform total of n comparisons. Hence, time complexity becomes order of n. But with the help of binary search, we can do the same task by doing maximum log n comparisons, and hence time complexity reduces significantly and becomes order of log n. Now we have understood the need of binary search. Now we'll move to the most important part, that is our approach. So now let's understand our approach with the help of example. Suppose we have been given an array A which is sorted in increasing order. We have 10, 20, 30, 40, 50, 60, 70, 80 and 90. We have total of 9 elements, n is equal to 9 here. And we need to search for the key 30 here. So what we will initially do is, we will maintain 2 pointers, start and end. We'll initialize our start pointer to 0 and we will initialize our end pointer to n-1. Initially we initialize our pointer to 0 and we initialize our end pointer to 8. Each time we will find a middle element. Why middle? You will understand it in few minutes. What will be the middle? Now say that initially our start is pointing to the first element, our end is pointing to the last element. In each iteration, this is talking about the first iteration. In each iteration, we will find the middle element. Here, middle element is 4th. So a of 4 is equal to 50. Now we will compare it with our key, which is 30. 50 is greater than 30. So, listen carefully. We can be sure that since our array is sorted, so we can be sure that all the elements including 4 and to the right of 4 will be greater than the key. That's why they are of not of our use. So if element at the 4th index is 50 and our key is smaller than that index, so we want to move to left side, because since our array is sorted, all the elements to the right of 50 will be greater than 50. So there is no use going towards the right. Therefore, what we do is now we don't consider this part and we come back to this part. That is, we initialize our end to mid minus 1. Now our end becomes 40 because the entire array is of no use to us. Therefore, in second iteration, our start is 0, our end becomes 3 and our mid becomes 0 plus 3 by 2, which is 1. We check a of 1 is equal to 20 is less than key. Means our answer will write to the right of 20. So all the elements to the left of 20 are of no use to us. Means now this array is of no use to us. So we neglect this array and we move our start pointer to 2. Now we have our start pointer pointing here, end pointer pointing here. Now our middle element is 2 plus 3 by 2, which is 5 by 2, which is element number 2. We check a of 2. It is equal to 30. It is equal to our key. Therefore, we return mid as our answer. Because when we find out the mid, a of 2 is equal to 30, which is equal to our key, and therefore we get our answer. I hope it is clear now that how this algorithm is working. If it's not clear, we will try to understand it with the help of pseudocode first, and then we will dry run it over one more example. Let's firstly have a look at the code. Here is our code for binary search. Firstly, in binary search, we are receiving two elements. We are receiving three inputs: int n, number of elements in the array; int star arr, it's our array in which we want to find, and here x represent our key. X is our key, this is our array, and this is number of elements in the array. We initialize our start to 0 and to n minus 1, and I will explain this condition in just a minute. Look at the code, what we were doing. We calculated mid, start plus n by 2. Firstly, we compare that if our x is equal to array of mid. If that is the case, we simply return mid. Case 2 were if x is greater than array of mid, means our key is greater than array of mid, means our left part is of no use. Therefore, we put start is equal to mid plus 1. Otherwise, else means its key is smaller than array of mid. Our right part was of no use. Right part was of no use. Therefore, we did end is equal to mid minus 1. Now, talking about this condition, while start is less than equal to end, let's consider a case. Now I will write it over a case where our key is not present. Suppose we do have an array 1, 5, 6, and 8, and our key is say we want to search for 10, say 10. Now what we will do is we will follow the same approach. We will firstly initialize our start to 0 and to n minus 1, and we will find the mid. What will be the mid? It is obvious that it will be 3 plus 0 by 2, it is v1. Now we will compare 1 here mid with our key. 5 is less than 10, therefore we need to move to right. Therefore we did start is equal to mid plus 1. Now our start is 2, our end is 3, we will again find mid. What our mid will be? Our mid will be 2 plus 3 by 2, that is 5 by 2, that is 2. Now we will compare a of 2 with key. A of 2 is equal to 6 is less than 10, therefore move to right, that is start is equal to mid plus 1. Now start is here and is also here, therefore our mid will also be this. Now again we will compare 8 is less than 10. Now again smaller, again move to right. Now our start will point to 4 and end is 3. It means our start of array has increased our end, It means element is not present in the array, and we simply return minus 1, indicating that element is not present in the array. We are doing here the same. While start is less than equal to end, we did this, and if not, we return. Now, having understood the code, let's have a look at the time complexity. We can easily analyze that in each of the iteration we were discarding either the left part or the right part. So we can say that if the initial size of our array was n, after first iteration it becomes n by 2, after second iteration it becomes n by 4, after third iteration become n by 8. Then suppose we performed k of such iteration in the worst case to get our answer. So the array size will become in the kth iteration will be n power 2 power k. So we can say that initially our size was n, then it reduced to n by 2, then it reduced to n by 4, then it reduced to n by 8, so on and so forth. We can rewrite it as n, it reduces to n power 2 power 1, then it reduces to n upon 2 power 2, then it reduces to n upon 2 power 3, and suppose we performed k such iteration. So in the last iteration our array size will be n upon 2 power k. But we can say that in the worst case, if we traverse the entire array, at the last we will be left with only one element. Therefore, after k iteration, our size will be n power 2 power k is equal to 1, n is equal to 2 power k, and k is equal to log base 2n. Means in the worst case, we perform k iterations where k is equal to log base 2n, and in each iteration we were doing a constant amount of work. We were calculating mid, we were comparing it, we were calculating mid, we compared it with key, and we update start and end. So what we can say that our overall time complexity becomes order of log of n, log of 2 base. It is written over here. Suppose initially array size is n, array size become n by 2 in iteration 1. After iteration 2, array size become n divided by 2 power 2. Suppose in worst case we perform k such iterations. So in the k step, array size become n divided by 2 power k. So in worst case, we will get our answer when only one element is left in the array. That is n divided by 2 power k is equal to 1, n is equal to 2 power k is equal to log base 2n. And in each step we perform constant amount of work. Therefore total time complexity is equal to order of k is equal to order of log n, which is much less than order of n, which was in linear search. Now talking about space complexity. Since we are using only variables like start, end and mid, and they take constant space. Therefore, we are not using any extra array or vector. Hence, our space complexity constant, that is order of 1. That is order of 1. So, our time complexity becomes order of log n, log base 2n, and our space is still order of 1. So, we will discuss some points to remember. Before applying binary search, we must be clear that array is sorted. We must know it's about its time complexity, that is order of log n. We must know about its space complexity, that is order of 1, which is constant. I hope now you have understood binary search in detail. I will provide the link of these notes in the description below. You can download those, and if you have any doubts you can comment it down. I will try to answer all the queries possible. Thank you. Have a nice day.